Have you ever wondered about the nature of numbers that can't be expressed as simple fractions? This question nudges us towards the enigmatic world of irrational numbers. Unlike the familiar territory of whole numbers and fractions, these peculiar numbers refuse to be neatly packaged as ratios. They are the rebels of the numerical world, shattering our preconceived notions of what numbers should look like. Imagine a number that goes on, indefinitely, without repeating itself. Numbers like these, that have non-terminating, non-repeating decimal expansions, are known as irrational numbers. They're like a never-ending story, a numerical journey that goes on forever without ever settling into a predictable pattern. This infinite, non-patterned sequence is one of the defining characteristics of irrational numbers, setting them apart from their more predictable, rational counterparts. But don't let their name fool you. These numbers aren't irrational in the sense that they're illogical or nonsensical. They're perfectly logical within the realm of mathematics. The term irrational merely signifies that they can't be expressed as a simple fraction. Perhaps you're familiar with some of the more famous irrational numbers. Pi, represented by the Greek letter pi, is the ratio of a circle's circumference to its diameter. It's a number that has been fascinating mathematicians for thousands of years, its infinite decimal expansion beginning with 3.14 and continuing unpredictably from there. Then there's e, the base of the natural logarithm, a number that pops up in many areas of mathematics and science. Like pi, e is also irrational, its decimal expansion beginning with 2.71 and continuing infinitely without repeating. The irrational numbers, with their infinite non-patterned sequences, challenge our conventional notions of numerical order. They invite us to delve deeper into the mathematical universe, to explore the hidden complexities and profound mysteries that lie beneath the surface of our everyday numerical understanding. They remind us that mathematics is not just about solving equations and crunching numbers, but also about probing the unknown, pushing the boundaries of knowledge, and unveiling the extraordinary beauty hidden within the ordinary world of numbers. The story of irrational numbers begins in ancient Greece, where the square root of 2 was found to be irrational. This discovery was a seismic event in the world of mathematics, sending shockwaves through the established understanding of numbers. The Pythagorean school, a society devoted to the harmony of whole numbers, was presented with a conundrum that challenged their core beliefs. The Pythagoreans held the conviction that all numbers could be expressed as simple fractions. The concept that numbers existed outside this framework was not just unsettling, it was heretical. The discovery of the square root of 2, a number that could not be expressed as a fraction, brought about a crisis in the mathematical community of the time. Imagine the shock and bewilderment as these mathematicians grappled with this new, irrational reality. Their mathematical universe, once thought to be a harmonious symphony of rational numbers, was now disrupted by a discordant note. This unexpected revelation was a jolt to their system, a glitch in the matrix of their understanding. The square root of 2, now known to be an irrational number, was like a black hole in the universe of mathematics. It was an entity that couldn't be defined by the existing rules, a number that defied the very foundation of their mathematical principles. This crisis was not just about a single number. It was about the very nature of numbers themselves and the framework that the Greeks had built to understand them. This upheaval also marked a turning point in the history of mathematics. It was the moment when mathematicians started to question the boundaries of their understanding and explore beyond the familiar terrain of rational numbers. This was a step into the unknown, a leap into the abyss of mathematical complexities. The discovery of irrational numbers opened up a new world of mathematical possibilities, and it challenged mathematicians to expand their horizons. It was a call to adventure, a beckoning towards uncharted territories in the mathematical landscape. This historical context sets the stage for the ongoing intrigue surrounding irrational numbers. The discovery of the square root of 2 was the first step in a journey that continues to this day, as mathematicians around the world delve into the mysteries of these fascinating numbers. The study of irrational numbers reveals a rich interplay between algebra and geometry. It's like a dance where algebra and geometry twirl around the floor, hand in hand with irrational numbers, each step revealing more about the complex nature of these mathematical entities. Take, for instance, the discovery of irrational roots in quadratic equations. You see, quadratic equations are those that can be expressed in the form x2 plus bx plus c equals sine 0, where a, b, and c are constants. Now, these equations often have roots that can be rational numbers, but sometimes they surprise us with roots that are irrational. Consider the equation x2 equals sine 2. The roots of this equation are 2 and 2, both of which are irrational. This was a departure from the familiar realm of real numbers, and it shook the very foundations of our mathematical understanding at the time. But how do we navigate this unfamiliar territory? That's where algebraic techniques come into play. By manipulating equations and expressions, we can unlock the secrets of these irrational roots. We can use algebra as a key, turning the lock on the mystery box of irrational numbers. Yet, algebra isn't the only tool in our arsenal. Geometric interpretations provide another lens through which we can examine irrational numbers. Picture a right-angled triangle with sides of length 1. According to Pythagoras' theorem, the length of the hypotenuse is 2, a visual demonstration of an irrational number. This combination of algebraic techniques and geometric interpretations allows us to explore the intricacies of irrational numbers. It's as if we're detectives, using every tool at our disposal to scrutinize the evidence and solve the mathematical mystery. And what do we find in our investigation? New insights into the relationships between irrational numbers and other mathematical concepts. We uncover connections and patterns that deepen our understanding of the mathematical universe. These techniques have become essential tools for exploring the relationships between irrational numbers and other mathematical concepts. So, let's keep dancing with algebra and geometry, twirling around the floor of mathematics, and uncovering the secrets of irrational numbers. Irrational numbers find applications in various branches of mathematics, from calculus to number theory. As we delve into the role they play in these areas, we'll see just how integral they are to our understanding of the mathematical universe. Let's start with calculus, a branch of mathematics that is fundamentally about change and motion. When we examine the curvature of a line or the slope of a curve, we're often dealing with irrational numbers. They're key players in the concept of limits, where we approach a certain value but never quite reach it. Think about the number pi, an irrational number we encounter when we calculate the area of a circle or the circumference. In calculus, it's the irrational numbers like pi that help us understand the continuity of curves and the concept of infinity. Now, let's turn our attention to number theory, a branch of mathematics devoted to the properties and relationships of numbers, particularly integers. Here, the irrationality of numbers like the square root of 2 or the golden ratio, phi plays a significant role in the distribution of prime numbers. The non-repeating, non-terminating nature of these numbers adds a level of complexity that challenges and enriches our understanding of number theory. And then, there's the concept of mathematical infinity. It's a mind-bending concept, isn't it? But it's in this realm of infinity where irrational numbers truly shine. If you've ever wondered how mathematicians can work with infinity, think about the infinite decimal expansions of irrational numbers. They never end, they never repeat. A perfect representation of infinity within the confines of a single number. It's these irrational numbers that help us grapple with the concept of infinity and make it manageable. We see then that irrational numbers are not just abstract concepts. They're tools, essential instruments that mathematicians use to explore and understand the complexities of the mathematical universe. The transcendental nature of certain irrational numbers contributes to profound insights into advanced mathematical theories. Their mystery, their allure, and their utility combine to make them a cornerstone of mathematical exploration, from the ancient Greeks to the mathematicians of today. The mystery of irrational numbers extends beyond the theoretical realm, finding unexpected relevance in real-world applications. One such application is cryptography, the art of writing and solving codes. Cryptography is the backbone of secure digital communication, from online banking to confidential government correspondence. The unpredictable nature of certain irrational constants plays a pivotal role in this field. To create a secure code, we need numbers that are as random and non-repeating as possible, a perfect job for our mysterious irrational numbers. They offer a level of security that would be hard to achieve with simple rational numbers. By using these irrational numbers, we can create codes that are incredibly difficult to crack, ensuring the safety of our digital information. The intricate dance between theory and application underscores the far-reaching implications of understanding the mysteries inherent in irrational numbers. As we dive deeper into these mysteries, we find ourselves more equipped to navigate the digital world safely and securely. In conclusion, the enigma of irrational numbers continues to beckon mathematicians into unexplored territories. From the ancient Greeks wrestling with the square root of 2 to the ongoing intrigue of their non-repeating, non-terminating decimal expansions, these mathematical entities keep us on our toes. We've seen how their study challenges our conventional notions of numerical order and propels us into a realm beyond the familiar. The interplay of algebra and geometry, the exploration of irrational roots, the enchanting dance of irrationality with calculus, and number theory all contribute to this rich mathematical tapestry. Not confined to the abstract, irrational numbers take a bow on the world stage too, finding relevance in areas as diverse as digital cryptography. Indeed, the mystery of irrational numbers is not just a question of pure mathematics, it's a journey that brings us face to face with the unexpected, illuminating the intricate connections that bind the abstract to the tangible. As we delve deeper into the mysteries of irrational numbers, we not only illuminate the abstract realm of pure mathematics, but also uncover unexpected connections that resonate in the real world.